thanks for having me. So my name's Aedan Callaghan. My background is in materials engineering, and I'm Plytech's Director of Mass Timber Acoustics and Technical Services. I've been in the role for about 3 years, and in that time been able to work on getting close to about 100 mass timber projects across North America, and even getting to see some internationally as well. Plytech's a Canadian manufacturer of acoustic isolation products. Really, we're a team of engineers that focus on sound and vibration isolation. So really anywhere in the built environment that noise is being created and there's another space where that sound or vibration isn't wanting to be heard, that's what we try and provide solutions for. And also on the sustainability side, really trying to use post-consumer recycled materials in that effort.
That's amazing. So I think everyone be interested in the dark arts of acoustics. So maybe we'll just go with the Acoustics 101, assuming people listening got no idea what's that saying. Tell me as if I'm a 5-year-old or something like that. But let's start there.
Yeah, so in building acoustics, there are two types of sound transmission. There's airborne sound and there's structure-borne sound. So airborne sound is going to be things like people talking, music being played, a TV on, a baby crying, and that is going to be sound waves going through the air. Those travel through any kind of partition and reach an adjacent space. When those sound pressure waves hit our eardrum, that's what we hear as sound. Structure-borne sound is a little different in that it's generated by some type of impact event or vibration source. That actually causes the structure to vibrate, and then when it reaches any kind of surface, a wall, a floor, a ceiling, it causes that to vibrate on the other side, and that generates those sound waves in that space. Again, reaching our eardrum and being heard as noise in that other area.
Amazing. And this is, so you got vibration, which is a structural check, and then you've got vibration in this context. Are we talking about something similar, or can you distinguish between the two?
Yeah, they're inherently tied, but obviously two different things, and sometimes can fall into two totally different scopes of a project and have two totally different engineers responsible for them. Like you mentioned, there's a definite connection between the two. Vibration tends to be considered things that are felt, whereas sound and noise are things that are heard. So there's kind of that line between what our body feels and what our ears hear. It tends to be around 20 hertz is that kind of crossover point. And so structures suffer from both. There can be the vibrations that you're feeling, that it's never a comforting feeling when you feel a building shaking. But then there's also, if there's footsteps above you, that would be in the audible range, more around like the 100 to 150 hertz range. And that's going to be those thuds that you're really hearing when someone's stomping around upstairs, often in a wood building or a lighter mass structure like timber.
Gotcha. So it's like, I'll play it back to, so the frequency, it's about the frequency, and then some frequency ranges is like a sound thing, and some frequency ranges is like a feeling thing. Is that
Exactly. Yeah, there's really the two properties of sounds that we concern ourselves with. There's the wavelength or the frequency, which determines if we hear it as a high frequency, high pitch sound, or a low frequency, low pitch. You can think of your piano keyboard, leftmost key, low frequency, low pitch, rightmost key, high frequency, high pitch. Those two sounds could be at this exact same sound pressure level or sort of decibel level, but we'll hear them differently based on the frequency. But then there is also just the amplitude or the sound pressure level of that noise. And that's kind of like the amplitude of the wave. So when we talk about sound, we're talking about the decibel scale. So a really good thing to remember in acoustics as well is that it's not a linear scale. When we are talking about sounds and going from 50 decibels to 60 decibels, that's actually on a logarithmic scale. So just like with the Richter scale and earthquakes, you might hear those two numbers and they sound pretty close together, 7.2 or 7.6. You'd think it's not that significant as a percentage, but because it's logarithmic, it can still be very substantial. So in acoustics, a good rule of thumb is that each 10 decibel change is going to be heard as twice as loud. So going from 50 decibels to 60, we'll hear as twice as loud, 60 to 70, twice as loud again. So it can pretty quickly spiral and sort of compound on itself to produce a very different sounding environment.
Gotcha. That's amazing. And so you mentioned a few different things like airborne and structural born sound. What are some of the principles to basically overcome them? Is there two different strategies for the two different types of sound, or is it the same sort of one hit, one kill sort of approach?
Yeah, no, it's a great question. So they are two unique types of sound transmission and often do require two very different approaches. A good example I like to use is for airborne sound, the biggest two drivers are mass and decoupled mass. So just the overall mass of an assembly is going to often dictate how effective it is at reducing how much you're going to hear the people talking or the music. So if you take a 6-inch concrete slab and were to double the thickness of that up to 12 inches, similarly for mass timber, if you double the thickness and the mass of that panel, you will effectively reduce the amount of airborne sound getting through that by about 6 decibels based on mass law. But a lot of the vibration, the high heel clicks through concrete, are not well impeded through that at all. So just increasing the depth isn't going to change how some of those footfall sounds transmit through. So that's where a different approach would be needed. So helping one is important, but might not help the other. So taking an approach that addresses both sides of it, the airborne and the impact sound, are both pretty critical to create comfortable living environments.
Gotcha. So if we were to decoupled, so maybe explain what you mean a little bit more about this decoupled concept and what that actually looks like if we're looking at a build-up.
Yeah, so that's where I start getting really excited about the possibilities with mass timber because, for example, if you take a 175 millimeter CLT panel and were to just direct pour concrete on top, you'd be looking at probably needing about 100 millimeters of concrete directly on that timber to reach what's typically minimum code for the airborne sound attenuation for a multifamily building. So it's a lot of concrete being added to timber. But what we can do is by actually better separating those two masses. So we add decoupling or add our Plytech GenieMat products to separate those elements. They start behaving as two separate masses. It's kind of like a mass on a spring. And so you can actually greatly reduce how much concrete would be needed down to often 50 millimeters, having that on an isolation layer rather than just using more mass, but directly attaching it. So that's kind of that principle of decoupling the mass layers of the structure.
Amazing. So one of the things with, I mean, other disciplines like structural engineering, it's like you can get a design guide, you got a calculation routine, pump in engineering properties, and then you've got your design. Similar thing with fire. Sustainability is pretty similar. EPDs, pump it through your mass, you get out your outputs. Is acoustics similar to that in a different category? And how much can you do by first principles calculations and how much is testing? Because I guess there's two different approaches. Can you maybe unpack both basically and how do you actually determine the acoustic performance?
Yeah, so for determining the acoustic performance, it often is, there are some first principles that I can touch on that are beneficial, but a lot of times it really gets into having a tested assembly as that starting point. So to have a tested assembly for airborne sound attenuation for under ASTM, that would be an STC rating, or under ISO, that would be an RW. But that would be essentially having a speaker on one side of that partition, either one side of a wall or one side of a floor ceiling, and it transmits basically a pink noise. It's like static that the radio, when it's not tuned, would give off, but just with very specific amounts of sound at the different frequency levels and a bit more low frequency content. And then there's microphones measuring on the other side. Whatever that delta is effectively telling you if what level of insertion loss or transmission loss that partition is providing. So how much does it reduce the sound down? And that's measured at a number of different 1/3 octave bands. But essentially it's telling you how much quieter it makes it with the same level of sound. For impact, we don't have a known amount of sound to start from. We actually it's trying to simulate footsteps. So there's a tapping machine, as it's called, and does essentially that, just has these hammers that tap down on the flooring. Quite noisy when the tests are going on. And then again, microphones just like measuring for what the sound pressure level is in the receiving space. Those two tests are kind of the standard for getting your performance of your assembly. Acoustics are, like you kind of said at the beginning, a bit of a dark magic. There's still a lot of mysteries kind of to how I think sound and vibration behave that keeps, I think, the world a bit exciting and interesting. But what it means is that having that starting measurement really is the baseline. I mean, when mass timber first came out, there are some prediction methods and modeling softwares available, but there was a lot of sort of wide-ranging results being spit out. So through testing, we can start to hone some of these calculations. There's, for example, mass law that dictates the airborne performance of an assembly. There's the ISO 12354 calculations, which actually are for flanking of an assembly, a separate topic that we can maybe get into. But when you're looking at the performance, it's normally looking at a tested assembly to begin with. There are some single parameter variables that can be quite accurately modeled, but anything varying too widely from a test starts to introduce, I'd say, quite a bit of uncertainty just in the way that sound can sometimes behave.
Yeah, well, there's a few things that I might double click on that one because it's one of those things like I've got a lot of experience in fire. I'm not a fire engineer, but like the just general principles of structural adequacy. And it's one of those things like you obviously need fire tests to determine performance. But if you fire test every single detail, it gets really expensive. So it's like, what's the right level of interpolation, extrapolation from tests that are based in reality that don't go off with the fairy sort of thing. So, you're mentioning on tests, like what is the right level of flexibility you can get post-test? Can you swap between suppliers? Can you swap between materials? Like what is those bounds of flexibility you've got to play with after testing?
Yeah, the biggest thing there is really having the data at your disposal to see what kind of variations we're talking about. So for the timber panel, for example, we've looked at cross-laminated timber, dowel laminated timber, nail laminated timber, all the various different panel types to see how those behave, different species, wood species type. And one of the big questions has been, as potentially more hardwood might get introduced into CLT panels, what's that going to do to the acoustic performance? And there's some hypotheses out there, but until there's enough test data to really prove out that hypothesis, it kind of relies on that testing. So when we talk about what the right amount of interpolation is, I think it kind of is looking at what the boundary conditions of your test data set are. We always try to test 4 different finished floor types, for example. So just changing out a vinyl plank, a laminate, a hardwood, a ceramic tile, looking at all those different floor types, looking at just a slight variation in one of the underlayment thicknesses, but controlling all the other variables. So really trying to understand what each one component's doing, because as soon as you start mixing and matching multiple, you could be attributing a performance change that one component was causing to something else. So yeah, that's the approach that we would often take with sort of our interpolations and calculations.
Yeah, it makes a lot of sense. And I think you might have, because we had lunch late last year in Seaford, actually, you came to Australia and you obviously got an active interest in Australia, New Zealand market, which is awesome. We'd love to have Apply Tech here in a big way. But, I think we were talking about the testing, like some places you have post-occupancy testing where like, obviously the risk of that, if you don't do it right, it's like expensive. I would imagine if you don't pass, and some places it's I don't know what the word would be, but pre-occupancy maybe. But you know, what are the different places have that? What are the implications of that? And you know, to reduce the overall risk of compliance risk, I guess. And is it the same globally and internationally?
Yeah, no, there's a lot of variation in what the building codes of different areas require. And I mean, I guess to just start off with, the building code for acoustics really is, I think, meant to be a bare minimum. There was a study done back in 2010 by the International Code Council, and they deemed that minimum code for acoustics in a multifamily building is really insufficient to meet occupant needs. In the US, for example, IIC 50 is the minimum requirement and STC 50. If you're living in an IIC 50 building, you can still clearly track where the footsteps of someone above you are. You by no means have sound privacy in your unit. So that kind of just sets the table there. So when we're talking minimum code, I think it really is a minimum. But then also to your point of what's required after the fact, different jurisdictions have very different requirements. So in the US, the most common path to code compliance is lab testing to the standards of STC 50, IIC 50. In Canada, we have ASTC 47 as our minimum code requirement. And what that means when you go to ASTC is that's the apparent sound transmission in the space itself and takes into account flanking and the actual in situ performance. In the UK, I know a lot of projects that we've worked on there have a requirement to post-completion test up to 10% of the units in a building. So really doing quite serious quality control, looking at did the building meet what the design was. The other thing that's kind of good about that, and I hope more and more will come of, is having that feedback cycle. So when we don't post-completion test or get data of how something did end up, you lose the ability to feed that data back into the design. So a lot of the acoustic engineers that we work with never actually get the ability to understand, was it designed right to the dot? Was it over-designed? Was it under-designed? So hopefully we'll move towards a world where there is more of that feedback to really get to the right level of acoustic performance, which is a subjective thing with one person having one tolerance, another person having another one, but at least I think designing to give people more privacy in their own homes.
Yeah, that's awesome. And before you mentioned a little bit about flanking, I think it's worth touching on why is this important? And then is it one of the most important acoustic considerations? And also just touching on from a multidisciplinary point of view, the need for teamwork, because I believe it's the junction sometimes where you've got different disciplines. If they overlook one another, then it you might have suboptimal outcomes.
Yeah. Flanking in mass timber is critical to the success of a project and kind of adequately designing for it and detailing it. And we always recommend having an acoustic engineer on board in the design team as early as possible, because that really does, I think, set the project up for success. It's a bit of a make or break thing when it comes to sound, is having that independent engineer working on things from an early stage. The big reason that flanking is a challenge in mass timber more so than other structure types is just that we have a lighter weight material and it's often exposed and often can sometimes even be continuous between units. So when we talk about flanking, essentially that is any path that sound can travel that's not the direct path right through the wall. So the wall that's behind me, if someone's trying to work or in a quiet meeting on the other side, there's a few ways that sound could be reaching that space. There's just directly through it, but then there's also through the ceiling and across to the ceiling of the other side. That would be the ceiling flanking path. Can also transmit or flank through the floors. So having all of those flanking paths understood and sort of quantified is important there, because no matter how effective the STC rating on your wall is, it might not matter if the weak link is the ceiling. In mass timber, if you have a 3-ply CLT that is continuous across apartments, then and exposed on both sides, my voice, any kind of sound can cause that wood to start to vibrate. Those vibrations can travel across that partition and re-radiate into the space. So you could have an STC 64 wall with a really well isolated double stud wall with isolation clips, having about as much decoupling there as you could. But if that's exposed 3-ply CLT runs across, you're probably barely going to meet minimum code, if at all. So that becomes a pretty challenging condition.
Is it implicit in saying 3-ply CLT specifically, if you added as much mass on that, maybe you could get around it? Is it that sort of thing if you didn't have discontinuity?
Yeah, so the reason I say 3-ply CLT is and continuous is, again, sort of for that worst case.
Yeah.
We've worked on some projects where the Genie mat has been installed on top of a 5-ply CLT with a topping, where the data is showing that you might actually be able to get to a point of minimum code or a bit above for your STC rating with the exposed ceilings. But again, it's something where until there's enough data, taking the conservative approach is always the best one. But we're working hard to try and get more and more data and post-completion data, also flanking data on those partitions to isolate them and, yeah, sort of show the performance meets the requirements.
One of the, I mean, as we're getting towards the end, one of the things that everyone's interested in always is the cost side of things and the trade-offs with acoustics. So I've heard anecdotally, like some projects are doing it for the first time, and it's just like overlooking the costs on acoustics, and then it just comes through and get a bit of a shock and frightened. Is that normally the case, or is it just tell us about the trade-off between good acoustic solutions and cost overall, and maybe we'll just over to you on that general topic.
Yeah, I think there's definitely an element of you get what you pay for, as there is in most things. We had a project where it was interesting because a developer came to us after the fact saying that they really disagree with the term value engineering. I don't know if you have that term
Yeah, we do.
in Australia, but it's pretty prevalent in North America here, VE-ing, saying that as an industry, as a construction industry, we've kind of changed what that means. It used to be finding value in equivalent solutions, but now it has essentially become just cost cutting.
It's almost the opposite of just, it's become removing value from project or something.
Exactly. And yeah, exactly. And so they had the project that this developer had worked on had basically been cost cut to a point that when they walked through the building, it was like, they're like, this is not what we wanted to be building. We wanted luxury level acoustics, and that's not what we're getting here. So the problem is that it's a challenge because once you reach that point in construction, there's not a whole lot that you can do. Some projects have switched to carpet last minute because otherwise the impact sound was just going to be too great. But if the sort of proper level of acoustic performance is designed in from the get-go, then having the isolation, having the proper thickness of Genie mat beneath the topping or beneath the subfloor can allow for hard surface flooring and still meet the sort of proper acoustic performance levels and proper IIC ratings. The challenge with acoustics, I find, is trying to explain something to someone that they can't see. We're talking about something that gets embedded within the construction, and you're never going to see it after it's installed. And hopefully you're never going to hear about it either. The best projects for us are the ones that we never hear from again, because that means no one even knows that the product is working properly. A lot of projects, if they just put down an 8mm rubber in the gym, for example, for cost reasons, as soon as people move into the units 1, 2, 3 levels up, someone's dropping a weight, then now all of a sudden the developer understands the value of a thicker gym floor system. But until someone had heard that and experienced it, no one could understand what that dollar value was going towards.
100%. Like if you think about other disciplines like fire engineering, everyone knows exactly what fire is and what will happen if a big fire goes off. But Yeah, you're right. Acoustics, I'm probably guilty of it as well sometimes. It's the start, you know what it is when you hear it only, but it's not something you're sitting there thinking about all day. You just notice it when it's bad, basically, right? And as you said, if no one's going to probably call you and say the pat on the back if it's working perfect. It's sort of like that's just by default if you don't get the call or something like that.
Yeah, exactly.
Yeah, awesome, man. Well, that's very well framed from a cost point of view because it is value, and like if you are trying to expose, timber and get the benefits of rental yields improvements from having a differentiated asset, a lot of the time we are hitting that premium market, and to go with great products like that. We're both pretty into the mass. I was about to say nerdy about the mass timber space. We probably are. What do you see as the future of this space? What's getting you excited as we move into the future?
Yeah, I think the two biggest things that I'm most excited about with it are the decarbonization efforts. One of the things that I actually get really excited about, and like you said, maybe nerd out a bit on, is when we get asked for one of our build-ups with Genie Mat on a mass timber assembly, and don't just get asked, what are the STC and IIC ratings for this assembly, and have you tested it? But when we get asked, what's the embodied carbon for that assembly? And having worked with our engineering team the past year as we went through getting our EPDs and seeing all the efforts that go into really understanding the carbon footprint of a material as it's produced, and being a company that really focuses on using post-consumer content in our products and recycling about 6 million car tires a year, seeing ways that we can build and also be looking at what are the carbon implications for this building, and really understanding that has been one of the things I'm most excited about. And then the other piece is just the rapid construction. I know, like in North America, there's a housing crisis in both Canada and the US. I think in Australia, you guys have a similar need for housing quite rapidly, and seeing how quickly these mass timber projects can go up really gets me excited about the possibility of just fast delivery for much needed housing, and doing it in a way where when you look at the staggering number of units that we need to build to get out of this housing crisis, if those were all built with concrete, we're talking about massive environmental emissions, massive carbon dioxide production into the atmosphere. So if we can solve that crisis and do it in a way that's sustainable, and we're really being conscious of the embodied carbon of these buildings as well, I think that's what keeps me sort of most excited about the growth in the industry.
Beautifully said, man. If people want to find out more about yourself and Plytech, some of the things we've been saying, where should they go, and where can people find you?
Yeah, so they can visit our website, email myself, or find me on LinkedIn. And if anyone listening to this podcast is going to be in Portland for the Mass Timber Conference, I know you said you're going to be there. I'll definitely be there. We're going to have a booth set up displaying a number of our acoustic solutions for CLT and mass timber. And yeah, really welcome anyone to come stop by and learn more about what we're doing and how we're trying to provide as low a carbon solution to these acoustic challenges in CLT.
Amazing. Thanks so much, man. It's beautifully said, and you've been awesome to chat to on the podcast.
You too. Thanks.